Hello and welcome everyone to the second session of SAT Vision organized by SEDS Sri Lanka in collaboration with SEDS SLTC. We are absolutely thrilled to have you join us today as we launch into this exciting new series. To help us make this event a reality, I would like to warmly introduce our official resource partner, Radio Society of Sri Lanka, and our venue partner, Sri Lanka Technology Campus. I am Tarun Nagaraja, representing the organizing committee of SAT Vision. I will be your moderator for today's session. Now, I would like to invite our project vice chairperson, Mr. Sadev Mina Prabhashwaran, to deliver the welcome address. Sadev Mina, over to you.
Good evening, everyone. It is my great pleasure to warmly welcome you all to the SAT Vision second webinar, organized by SEDS SLTC in collaborate with SED Sri Lanka Technology Campus, SED Sri Lanka, and Sri Lanka Radio Society. As the vice chairperson, I am truly delighted to see such as an enthusiastic gathering of students from both schools and universities, all united by a shared passion for space, technology, and innovation. Your presence here today reflects the growing interest and commitment of young minds toward the future of satellite communication and space exploration. SatVision is not just a project, it is a platform where curiosity meets knowledge and where ideas are transformed into meaningful learning experiences. Through this webinar series, we aim to bridge the gap between theory and real world applications in the field of satellite technology. Today, we are honored to have with us an exceptional guest speaker, Mr. Mike Shane Fernando, a respected, a respected member of Sri Lanka Radio Society and an engineer executive at Dialog TV. His expertise and industry experience will undoubtedly provide valuable insight and inspiration to all of us. I encourage each and every one of you actively engage, ask questions, and more make the most out of this opportunity. Learning is most powerful when we participate and explore beyond boundaries. Once again, thank you all for joining us today and being a part of this exciting journey. Let's make this session insightful and inspiring. Thank you.
Thank you, Sadev Mina. Now, it is my absolute honor to introduce our esteemed guest speaker for today's session. Joining us is Mr. Mike Shane. Mr. Mike Shane is a member of the Radio Society of Sri Lanka and is currently working at Dialog TV as an engineering executive. He will be conducting the second session on building your own ground station. Mr. Mike, the stage is yours.
Thank you to everyone. I hope I'm audible to everyone, and thank you for the nice introduction. So before we begin, I hope previous lectures, in the previous lecture, you have some basic idea about satellite. Obviously, you are like a satellite society. So I hope you have some basic understanding of satellites. So in this session, we are planning to do something about how to make a ground station. So basically, in this 2-hour session, we will try to cover mostly everything possible within the given time. So let's get started. Let me share my screen first. So this is the session 2, I guess, right? So it's about building a ground station. So has anyone ever been to like a satellite station? Obviously, your university also in like a previously commissioned satellite station. If everyone knows that is the biggest, it has the biggest dish in Sri Lanka, and we'll discuss about how the presentation will be moving on. So the outline, first we're going to talk about antenna types. So basically here we're going to talk about, usually, might have some understanding about antennas, and here we are mostly focused on about satellite reception. So we basically be talking more about satellite related stuff of antennas, and then the second one is about affordable receiving equipment. So basically here, when it comes to satellites, I mean, if you all know, the satellite receiving equipment are very expensive. Hope everyone can see my slides, right? Can someone?
The slides are visible, Mr. Ashwin.
Okay, sure. Thank you. So, like affordable, when it comes to affordable, I mean, when it comes to space, I mean, space stuff are like very expensive. So here, I mean, we try to use most of the like least expensive equipment. So basically, we are mostly talk about SDRs. Uh, and on the third section, we'll be talking about various means of tracking satellites. And on the fourth part, we'll be try to decode what we get from the satellites. And on the fifth part, there will be more information about the setbacks and caveats about receiving from satellites. So the first part, the antenna types. So as you know, I mean, with every signal, you need an antenna. That's the first part of the receiving system. So basically, when it comes to satellites, we can use parabolic dishes. So I mean, I think everyone knows what parabolic dishes are. So basically, they are the satellite dishes. We call them in the common name, and there's directional antennas. So basically, every time you don't need a dish for like receiving satellite data, sometimes you can use directional antennas. These antennas are more centric towards like a small beam. So basically they have higher gain than compared to like normal antennas, especially like Yagis. So the last one is circular polarized antennas. I mean, these antennas are like mostly used in satellite earth station, especially for weather satellites. Because I mean, some certain cases, tracking equipment are very expensive. So these circular polarized antennas are like a one solution for that tracking equipment. So basically here you don't need any tracking equipment. So basically this antenna itself is polarized. So it can receive the signal with some minimum loss, but a good signal without tracking. So basically let's move to several antenna types. So what do you need antenna for? Like receiving. So especially when it's receiving a satellite signal, you have to consider about several things. Do you have tracking equipment? So if you have tracking equipment, you can use a very powerful antenna like directional Yagi. And then you have to consider how far is your satellite. So basically, satellites are flying on different orbits. So basically, let's say there are geostationary satellites and there are low Earth orbit satellites, and there are some outer space ones. So basically, here we have to consider how far is our satellite. That way, we have to consider how much gain we need. Because I mean, when you take an antenna, there are higher gain ones. So basically, both tracking equipment and how far is your satellite is like very related. So basically, your amplification stages depends on those two criterias. And lastly, what frequency band? So basically, you can't use the same antenna for every frequency band. So for like example, for VHF band, you can use a different antenna. And for like high frequency, you will need a bigger antenna because the equation C equals F lambda. So the wavelength is very high when it comes to lower frequencies, and it gets not exponentially, like, it decreases with the frequency. So basically, you need a better antenna for your suitability. And I mean, in this case, for sat receiving. So I'm gonna ask you like a simple, not simple. I don't know whether you know the half of the meaning of this. I mean, still I'm gonna ask you the question. So let's say we want to receive WX images. So basically, when we say WX, here we call them as weather images. So basically, this is like an acronym for weather. So weather images via APT from NOAA 19. And the problem is you don't have any tracking equipment. Uh, let's say, I mean, can you like guess what is the most suitable antenna type? Anyone have an answer for that one? Uh, I mean, the answer is lie within here. So anyone try to guess? I'll promise there won't be any more questions down the road. So this is the only question I'll be asking. So I hope someone could answer.
Hi, like similar like turnstile antennas.
Yeah, that's correct. That's correct. That's another one. Actually, I mean, it's like a hybrid of like circular polarized antennas and like directional antennas. You're correct. Exactly correct. I mean, I was like going for the circular polarized antennas. I mean, but still, I mean, you gave a better answer. Actually, I'm impressed. I mean, so basically, you know some stuff about these antennas, and basically, you are a satellite group. So that was like unexpected answer, but that's very correct. I mean, it's like dipole, like mix of dipole and circular polarized. So thank you for the answer. I don't know what the name of the guy who has answered it, but anyways, thank you. So this is the solution, and his solution was correct as well. So if anyone is wondering, so there's this quadrifilar helix. We basically say QFH antennas for this type of variation. So I mean, on the right side, you see the antenna. I mean, seems like very convoluted type of antenna, very like funny looking, but still, I mean, this antenna is much more capable when you don't have any tracking equipment. So basically, let's say you are using like a radio base station for like weather satellite image receiving. So it's unmanned. So basically has less power. So and less equipment. If you use this type of antenna, you won't need any tracking equipment. So basically, this antenna is always polarized on every angle. So that's why it's like a helical type. So basically, I mean, if you like, you know, the actually EM radiation actually moves like this. So basically this like actual like representation of the wave. So by design circular polarized. And as I said, doesn't need any tracking equipment, and it's very budget friendly compared to like other tracking related antennas, and it has less moving parts. To be honest, there's no moving parts altogether, so you don't need any like expensive tracking stuff for this antenna. So that's why many of the base stations use this type of antenna. As in fact, this type of antenna is used in the satellite itself as well. So basically, you are mimicking the same antenna in the satellite, and that's the solution. And his turnstile antenna is also correct one. So let's move on to the other part. So basically, I mean, I went through the antenna part very quickly because I mean it's the least concerning thing I think you have, and there are like more things to like talk about when it comes to this that stuff. One of the most important thing is affordable receiving equipment. So basically, I mean, when it comes to satellites, everything is expensive, but I mean, these SDRs, I hope everyone knows what an SDR is. So basically, SDR means it's a software defined radio, it's the long term. So basically, this is like an radio. It is like connected to the computer, and it sends all the data like a normal radio, but all the processing is done within the computer itself. So basically, normal radios. I mean, you might have like used one. So basically, if we take like a commercial radio that we use to listen to FM, you can't use it to anything other than FM. But with the software-defined radios, what you receive is the baseband. So basically, this will like using a DAC. So sorry, ADC, analog to digital converter. This will like convert that signal into a digital form, the RF signal itself, and then it will move through a thing called quadrature modulation. So it will split the RF signal using a phase shifter. One is in phase, so basically it's the same signal, and another one out of phase 90 degrees. So basically this way we can measure the phase amplitude as well. So in a normal system we can only measure amplitude. Here we can use phase as well. So this is the most fundamental thing every software defined radio is based on. So quadrature modulation. So I'm not going to talk about quadrature here because we are like talking about how to build a base station. So basically I'll skip through the math part. And in this presentation, we will talk about RTL SDRs and AirSpy devices. So basically, I think everyone knows what RTL SDR means. I mean, it's a very cheap, I mean, technically it's a digital TV receiver. Somehow very smart people have figured that they can be used for receiving other signals as well. So they have developed softwares around this ecosystem, and this AirSpy devices is a derivative of this RTL SDR, but the AirSpy is much more capable than RTL SDR. So basically, if you are like more into satellite, I highly recommend first buying the RTL SDR and move into the AirSpy devices, because AirSpy is like much more capable when it comes to bandwidth. So especially when with satellite signals, what we mostly need is bandwidth, because normally satellite signals, unlike like AM and FM signals, have a very high bandwidth. Sometimes it's 200 kilohertz for, I mean, the stuff we talk about in this presentation today. And they can be like many gigahertz. Sometimes it can move to like 200 gigahertz, sorry, 200 megahertz to within that range. So basically, higher the bandwidth, the better. So basically, I'm suggesting if you like want to try this stuff, I mean, I'm talk about today, better start with the RTL SDR and move on to AirSpy devices. So basically, here are the two devices I'm talking about. The first one is a RTL SDR one, and bottom one is a AirSpy Mini. I mean, this AirSpy, there are like several versions, and this is the middle version. So basically, it has like 6 megahertz of panoramic bandwidth. So basically, the RTL SDR has only like about 2.4 megahertz of bandwidth. So it's not that, I'm not saying that it's not great, but if you can consider buying an AirSpy, it's a very worthwhile investment if you are really into this set business. And the price wise, I mean, this is very expensive, like 3 times of RTL SDR. So basically you can buy 3 RTL SDRs for the price of this one. So this one is about $99, and the RTL SDR is about $30 at this point. I think with the dollar rate, I think somewhat expensive. Uh, but with this AirSpy, they have some discounts, mid-year discounts, and Black Friday discounts. So if you like keep an eye on those stuff, you might able to get this one for like 25% off to 20% off. And let's compare the both devices. So basically, when I say sampling speed, it's mostly like bandwidth. So basically, the RTL SDR has about like stable. I mean, you can drive it much faster, like a little bit faster, but mostly it's stable around this sampling speed, 2.48 mega samples per second. And for the AirSpy, it has no problems with this sampling speed. It can go all the way to like more than this, but the stable bandwidth for like, since it's like still, I mean, even it's capable, the USB type is 2.0. I mean, if you know, USB 2.0 has like 480 megabits per second bandwidth. So basically, the ASPI Mini could drive faster, but you will drop frames if you go beyond the 6 megahertz range. And one of the most important thing about receiving signals is the noise flow of the receiver. So basically, an RTL SDR has a noise flow around minus 60 decibel to 70 decibels. So, and an AirSpy Mini, on the other hand, has like minus 70 dB to 80 dB. So even though it's like only like 10 dB of a difference, this 10 dB can make signal drown in the noise flow or will be visible. So basically, I mean, I hope you know what dB means. It's like a logarithmic scale. So 10 dB is a lot. So bear with me. I mean, the difference is day and night with these two devices. And there's this ADC depth. So basically, the ADC bit depth is like, as I said before, I mean, the SDRs depends on an ADC. So it's like an analog to digital converter. So, I mean, I think you know, I mean, every ADC has a bit depth. So RTL SDR has 8 bits and AirSpy Mini has 12 bits. So basically, even the numbers are like bit different, but this has more dynamic range because the bit depth is 12 bits. So basically, you can use this 8 bit, but you will saturate sometimes. I mean, if the signal is, I mean, has a higher dynamic range. When I say dynamic range, sometimes the signal can go like very high, and the next signal can be like very low. So on an 8-bit depth ADC, that difference can't be distinguished very apparently. So if you have more bits, you can distinguish that difference between the high and the low much more clearly. So basically 12-bit is like two times and more than better than an 8-bit. And this dynamic range is derived from this ADC bit depth. So basically, it's like same way of saying the bit depth. And this like regarding to a scale. I think you know, I mean, when you convert something to like digital, I mean, you can't go beyond zero. I mean, I don't know, you have know the actual term. I mean, zero is the maximum we can go in the digital realm of DSP. So basically, this dB here is like how below you can go from 0 dB, and that's that. And another thing is all these RTL devices have what you call an amplifier. So basically, each and everyone, I mean, know what, I hope everyone knows what an amplifier is. The thing is, I mean, even though these RTL SDR has this much of like dB of gain and the AirSpy Mini has this much dB of gain, most of the time the AirSpy Mini outrun the outperform the RTSDR because it has a lower noise flow. So basically, and it has a like a bit depth of 12 bits and a higher dynamic range. So basically, even though this has higher gain, I mean, if you send a very weak signal to AirSpy Mini, I can assure you, I mean, it will be decodable more clearly in an AirSpy Mini compared to an RTL SDR. And with the price, finally, everyone, if you want to buy, these are the prices. The RTL SDR comes with an antenna. So basically, I highly suggest use the kit RTL SDR. So you can like get started very quickly, and both have the SMA connector. So basically, they are like very fragile compared to some modern ham, like reliable ham connectors. So, but they are there because they are very small. But when you like go into the field, we use BNC and other type of connectors. But the thing is, these are like very like delicate devices. They use SMA connectors, and this is the kit I was talking about. This is a RTL SDR kit. Uh, I told you, I just checked the price today. This is the today's price on eBay. So you can get all of these stuff. So basically, I'll go through every stuff in this picture. Obviously, this is the SDR, and these are two sets of dipoles. So basically, I mean, they are affectionately called as bunny antennas. So basically, this is for like very like high frequency antennas, and these are for low frequency, basically like VHF and UHF. And this is the antenna connector, the V dipole, and this is a suction cup you can use. I'll I'll show you how to use this one in like a very like clever manner to how to track a satellite. And this is the SMA connector cable. It's like 2 meters. You have to like extend this one if you really want to try something. And this is like a tripod one. You can mount the antenna itself to some like a bamboo or like a pole, and you can raise it using this one. So basically, if you really want to get into this satellite world of decoding, I highly suggest start with this kit. Don't buy the only buy the RTL SDR. If you can get these all of this stuff, it's very worthwhile, and you will like get your decoding game very much higher compared to like only getting the RTL SDR. And another problem. Satellite signals are very weak, but for our favor, every SDR that is in the market has an amplifier. So this part is little bit invalid for this section because we are talking about NOAA and some other weather satellites. Actually, I have like a very sad news to tell you. I'm not telling you it like right away, so bear with me. And these satellites we are like planning to receive doesn't need like specifically built amplifiers. So greatly we can use the same amplifier within the SDR itself. So here the use of it's like very minimum, but still I want to show you how much amplifier can greatly benefit in some scenarios, because we planning to build an ADSB tracker in our like workshop. So let me show you the difference. So right side, on the left side, you will see an antenna without an amplifier. So basically, I want to show some quantitative measure because I can say this has this much dB of a gain, and you won't have any idea about how much of an impact it could make. So basically, that's why I've used this comparison. So this is ADSB receiver map, range map. So I've used a software called Virtual Radar. So it has this max range map. So basically, I have plotted a map without using amplifier. So here you can see it can't even like go to the like only like less than 100 kilometers of range without an amplifier. And on the right side, if you see, it's almost go to India. So that much of a difference can make how much of a difference can an amplifier, inline amplifier can make. See, if you see it, already tracking like an aircraft. It's like a Sri Lankan airline aircraft flying over 35,000. Tracks like at the very edge of the southern part of Sri Lanka. So that's how much of a difference it can make if you use an amplifier. But there's a problem. Always, if you think more gain is better, actually it's not true. With gain, if you have higher noise, you will lose that benefit of having gain because the amplifier doesn't know what signal to amplify. It will amplify everything within the amplifier's capability of bandwidth. So basically, you need some filters as well. So your setup will get little bit complex, but you will get better range. But first, you have to check whether you need an amplifier. In this case, you will definitely see the differences day and night. And but for these experiments, we won't need any amplifier. So I just want to like show you what an amplifier could do. That's it. We'll use this amplifier in our workshop for like ADSB receiving. For the set part, for now, we won't be using any of those amplifiers. We'll be using the inbuilt amplifier of the SDR itself. So, and another part of the puzzle is various means of tracking satellites. I mean, does anyone has an idea about how to track a satellite? I promise that I won't be asking any more questions. I mean, if anyone's willing to answer, they can answer now, but it's not mandatory. I mean, I'll wait like a few seconds and move on to the next section. If anyone has an answer, they can present now.
Tracking with like software tracking, mostly we do it, right?
Yeah, yeah. What kind of software? Do you know any software that, I mean, if
Using
you don't know,
using
Yeah,
using
Orbitron, same as that.
yeah. That's another one software. Yeah. Anything else? I mean, obviously you guys know about the set stuff. I mean, yeah. Tell, I mean, if anyone else with an answer.
Did you ask the
Okay, let's
decoder
move on to
also?
the what?
Did you ask about the decoder?
And we are still on the tracking part. Actually, I built this presentation from top to bottom. So basically, we have covered the end. I'm going through each and every like step of building a ground station. So basically, we have covered the antennas and we have covered the receivers. So now we want to know how to like know whereabouts of the satellite. So that's why I'm asking about only the tracking part. The coding part will be the next section.
Yeah, thank you.
I think I got like several answers. So let's move on to the next section without any further ado. So I mean, I have only like, I mean, this is my way of thinking. It's not like hard and fast rule. I just want to like make the thing simpler. So I'll be telling you how to use a mobile app. I mean, this mobile app will be our tracker. Like DIY tracker will be based on this mobile app itself and using computer program. So I'll be showing like several ways actually. So first, let's get started with this mobile app. And before that, I hope everyone knows, I mean, how to like say where a satellite in the sky. Does anyone know what this means? Elevation, altitude, azimuth. Anyone?
we need its orbital data.
Yes, exactly. I mean, after the orbital data, we need a way to like say it. I mean, orbital data has like very big, like complicated numbers. I mean, strings of numbers. but you can say, I mean, let's say, I mean, for a position in Earth, let's say your home. I mean, from your home, you can specify where the satellites within, I mean, if the satellite itself within your sky, you can say where the satellite with using two numbers, actually two angles. This is, I mean, there are several ways. Actually, here we use elevation and azimuth. So basically, most of the softwares, I mean, actually, not only softwares, one of the most easiest way of telling where a satellite within a given time on a given place, we can like say it using elevation and azimuth. So bear in mind, if you say, let's say from your home, this satellite has this elevation and this azimuth, it won't be valid to a different locations, like different elevation and azimuth to a different place. So basically, if you say this one to a different friend of yours, saying, hey man, I saw this satellite, it has an elevation about this much and azimuth about this much. I mean, when he is trying to like lock into that azimuth and elevation, he won't be seeing the satellite, especially if it's very far away, like 100 kilometers. So basically, what I want to point out here is this coordinate system we are talking about here. It's location specific. You can like be within like few kilometers, and this will be a little bit accurate. Beyond that, this system will like differ to a different location. So basically, this is like a easy way for us to like referencing to ourselves. So you can't like use this to like different stuff, because I mean, there are like different ways of like saying where the satellite itself is, because we are talking about base station, and there's tracking. So with this tracking, this azimuth and elevation is very important. I'll show you in the next slides, I mean, why is it very important. Let's move on to the actual app. Okay. I mean, I hope someone might know this app. I mean, it's called Sky Tonight. I mean, it has a paid version and a free version. I don't know whether you know. I mean, every year, I mean, on the day of astronomy, I think they have like a 50%, I mean, the paid version. So basically here, this is the passes for NOAA 19. I mean, in this app, you can like search for a satellite and you can get the passes for like up to like 1 week or so data. Here, there are like several passes within today. Actually, these all screenshots are taken today. So like from today onwards, I like getting much as possible data within the day. So it will be much more relevant than like 2 weeks ago before. So here, these are the elevations for today. Seems like there's a like a satellite overpass right after our lecture ends. So basically around like 10:10. So here I'll explain this app. I think it's better if you can like note this app down, because we'll be using it on the workshop. I mean, if possible, like search for this app. I mean, I know it's like it has a free version. You can use that one for our workshop day. So basically, kindly like if you can like download it before like coming to the workshop, that will be
Excuse
ideal.
me.
Yes.
Can't we use GPredict on the workshop?
Yeah. Actually, you guys are like way before. I mean, actually, the second software I was going to plan is GPredict. I think you have like went through my slides. Like, I mean, you guys telling the next stuff I'm going to plan. I mean, keep that flow. I mean, moving. I mean, it's very useful. I mean, it's very helpful for me as well. So basically, if you know, I mean, I think you can guess with these icons what this every icon means. I mean, here this icon means, I mean, when will the satellite will be rise, and this is the highest point. So in this case, the highest elevation, when at what time it will be the highest in the sky, and this is will be when it will be set, so zero elevation. And this sunlight thing, it's the brightness. I mean, I don't know whether you have watched the International Space Station. I mean, there's an app, I mean, dedicated app developed by NASA. They used to like send like emails. I mean, when if you like subscribe to their website, here this is the brightness of the satellite. Can anyone tell me this 9.3? Is it bright? Can you see it in the sky? 9.3. It's like a good number or a bad number. It's talk about brightness here.
It is not bright when we see by our naked eyes.
Yeah, I mean, there are satellites, to be honest, you can see with your naked eye, means like not the satellite itself, like a dot flying in the sky. So basically here, sadly, these weather satellites are cannot be seen with the naked eye. This 9.3 is saying that it's very dim, like very, very dim. You won't be able to see it with naked eye. But if you, I mean, if you download this app and go and see the ISS, search the International Space Station, you will be able to see it with your own eyes. If the sky is like very ideal and you are in a dark place, even I am at a town and I'll still able to see it. Plus, I'm near like the airport, so our sky is like very bright every day, 24 hours. So still, I was able to see the International Space Station. So these are the information you will be needed for the tracker itself. Uh, Bear in mind, I mean, this will be very important. That's why I have zoomed it and like make this part of more visible and explaining each and every icon here. And the next one is if you have a like a VR capable phone, I think mostly everyone currently have like a VR capable phone. I mean, accelerometer and a gyroscope. So this app can be used as to like point and see where the sky. I mean, point to like a place of the sky and you can see what there is it, and especially stars and in this case satellites. So that's the app I want to show you, and I hope I mean you can like download this app. And as you guys suggested, gpredict. Actually, this is my favorite one compared to Orbitron because this one has like some nifty features and it's much easier to use. So after like many years, I have reopened this program. So basically, all the TLEs means like a special like two lines of data that you can represent movement of the satellite for like within for like couple of days worth of accuracy. So basically, when you like starting gpredict, always it's good to like update these TLE files. So basically, I mean, there are like several websites and URLs. I mean, they constantly update these files. So basically, you have to like configure the gpredict itself to like use those URLs and download the new satellites. Here, I think I haven't used this for like an year. So basically, it has updated 11,000 satellites. So basically, all the stuff you see right here now is currently being updated. Here, if you see, I mean, in the morning, the ISS has passed like our Sri Lanka or Sri Lanka. I mean, can you guess? I mean, by the look of these footprints, I mean, can you like guess what get? I mean, guess what kind of satellites these are? It's like AO91, AO85. I mean, does anyone have
Like cube satellites.
any idea about what those satellites are? I mean, there's a little bit of hint here around the top corner.
CubeSats are a cube-shaped satellites.
Yeah. I mean, what are the use of those satellites? You can see the hint on the top part of the window. I mean, the screenshot itself. Actually, those are amateur satellites. that we can use as repeaters. But we are not going to talk about those stuff in this, this presentation. And there are like, if you like move on to your like bottom part of the screen, you will see like a crosshair with like several centric circles. I mean, there's this stuff called electro L3 and geo compass at 2A. What do you think those things are? Since we are talking about weather satellites, those two are like two very recent weather satellites, and they are like geostationary satellites. Basically, especially the electro L3 one. This is like, if you see, this crosshair, very middle of this crosshair is where you are. In this case, it's my location. From my location, this electro L3 satellites is like on the top of my head, like basically it's overhead. So if I have like a very good powerful dish antenna, I can receive this one. Sadly, all these geostationary satellites work in like a few several gigahertz range. So basically, for our workshop, we won't be talking about these stuff, but bear in mind, we will be have so much fun, but still, I want to say that there are more than satellites for weather. No, more than several satellites you can use for weather satellites. So basically, this Electro one is made by Russians, and GeoCompassat, I think it's a Korean one. And obviously, you all guys know what NOAA means. All I want to point out is, there are like several countries, they have like put satellites, weather satellites for use for themselves, and some satellites, they transmit over like specific areas. So basically, some satellites, like orbiting satellites, they only dump data, especially like highly sensitive, like high resolution image over their origin of country. So basically, let's say there's a satellite made by USA. They will send some data to us to receive. Maybe those images are scrambled and less resolution compared to the original capabilities of the satellite. But they will only dump those high resolution image over like a specific place, like a specific downlink Earth station. Other than that, they will only transmit like normal low res stuff. Mostly all of the satellites like that. Actually, with this like pose and everything, each and every country has realized the potential of satellites. So basically, most of the satellites right now are very far within range of amateurs like us. You will need like bigger dishes and higher expensive stuff to decode. So that's what I want to point out. I think everyone knows what G-predict is. Do you need an introduction? Because one has mentioned it. Do you need an introduction for that one as well? Hello. I think it's better to move on to that one then. Yes. Okay. Can you see my screen? Now I'm in the G-predict window.
Yes, sir.
Okay, don't call me sir. I'm like not a sir. Just just say yes. That will be fine. Okay, now we are in the G-predict window. So you can see. You can have like several sections. Sometimes you have like several interests. So basically this section, I have dedicated this part of the screen to like amateur satellites. To be honest, there are like two geostationary satellites in this part and the ISS, because ISS is also an amateur station because they have like amateur related stuff. I mean, Earthlink. So basically you can use like a normal ham radio and some good antenna, and you can use their repeater to like send voice to like a very higher footprint. Actually, I mean, if you see this like circular area, that's the footprint of the satellite. That's what the, if you are like within in the ISS, you can see that much amount of area of the earth. I mean, if you go to this side, if you like go to this electro one, I hope you can notice that I have selected the electro satellite, and the footprint is very high, Sri Lanka, but still it can reach Africa, like very end of the Africa. What do you think this satellite is? Is it a geostationary one or like a low Earth orbit one?
It is a geostationary.
Yeah, exactly. It's not even moving. I mean, compared to ISS, I mean, it's like moving, like very visible. It's moving. This one is very like still. It's like it's not station. It's not moving. Like very stationary. But to be honest, these also are like moving in like a small 8-figure pattern, but it's not a very big concern for us, or at least for us. I mean, but it's a different story if you are like transmitting to the satellite. So basically, when it's receiving, I mean, you guys know Dialog TV, right? I mean, obviously, it's like one of the main satellite TV providers. I mean, we always provided the customer with like a small dish, and the satellite is also a geostationary satellite. Anyone have an idea about uh, which side of this satellite is? I mean, where this satellite is? The Dialog TV satellite. It is like within top of Africa or around like Indonesia. Where is it? Can anyone guess? Because I mean, I just want to like not only talk about weather satellites, I want to like give much more information possible with giving time frame. So we want to like talk about like many stuff. I mean, can anyone like guess where the satellite is?
Mostly,
You can search it.
like mostly in
The satellite.
southwest.
Yeah, tell.
Mostly in southwest
Yeah. I mean,
directions.
yeah.
Around
In
60
the
degree
west direction,
upwards.
actually.
Yeah.
Actually, it's like OT. I mean, you are correct. It's westbound. So basically, it's around like near Africa. So if you guessed it correctly, this is like a better way to find if you are like disoriented in like in Sri Lanka. If you can see like a Dialog TV dish, I'm not promoting Dialog TV or anything here. Uh, you can find where is the west. If you see a dish, if it's pointing to the sky, that direction is west, because the satellite is on part of Africa. So that's like a very nifty trick if you like disoriented in a place that you are like not familiar with. If you see a Dialog TV dish, I mean, if you face that direction is west. So that's like some extra info for you. And as you can see, I mean, we are right now in the amateur radio satellite station part of our section. So basically, this is like modular type. You can add some more, like here. You can add a new module and it will pop up here. So basically, now I'm going to like move my attention to this part of the top right part. So here there are like several options here. Can you see those things? I mean, radio control, antenna control. I think everything is visible. I'm going to go to this radio control one. Okay. This is like a hypothetical frequency. This is like, I want to explain, there are like several things. I mean, you can know the frequency of a satellite, a downlink satellite, but there's a problem. Can anyone guess what this problem is? The problem itself within the screen itself. It's showing in the screen itself. Can you guess what it is? Anyone? Okay, the problem itself is Doppler effect. Since these satellites are like flying in like very high rate, I mean, if you can see here, this satellite itself is now cruising at 2.1 kilometers per second. So basically, it's like very fast. With this very fast moving objects, we have to be like more careful about how we like tune the radio. I mean, there's a base frequency. In this case, it's 145.89. So, but the thing is, if you like tune this frequency to your receiver, you might miss the signal. Not miss, but there will be some like, how do you say, like less accurate signal. You always have to account for Doppler when it comes to satellites, because without this Doppler correction, the frequency will drift. Actually, you can see it if you like, if you use some sort of like waterfall and spectrum, you can see the, if you like move from like, if the satellite itself is moved towards you, the frequency will increase. And if the satellite is moved away from you, the frequency will decrease. So here in gpredict, we have this nice little tool we can use to like uh, get Doppler corrected frequency for our given frequency. So basically here I have like put some like random frequency here. If you press track, let's say,
Yeah, excuse me.
yeah,
Yeah, may I
yeah.
know what waves does this use? Like
What you
sound
mean
wave
by
or radio?
wave?
Like sound wave or radio waves?
To be honest, I mean, if you, yeah, it's good question. Doppler effect is like applicable for all waves, to be honest. I don't know, in A levels, there's this nice little question uh, where the blue shift and red shift. So basically, if you see a star, I mean, there's this blue shift and red shift. So basically, you can find the uh, direction of spin with this blue shift and red shift. So basically, also here, I think you should better look up it one. That one is very interesting, especially if you are on satellites. Every electromagnetic frequency signal is affected by this Doppler effect. I mean, if you like wondering if it's only applicable for like sound waves, I mean, obviously we have like calculated those stuff in A levels for sound waves only. So basically that's very like very easy to misunderstood that a light wave doesn't behave exceptional for this Doppler part. Actually, it's very much affected to normal RF signal as well, because we are like here we are talking about very high speeds. If I think you have got your answer, if not, I think you can like further ask me questions. That will be fine.
Yeah, I got my answer.
So here the Doppler effect is for this speed, for this frequency is the corrected version is -843 hertz. So basically, if you reduce this one, you will get the Doppler corrected radio frequency. This is very important, especially if you like receiving SSTV, slow scan TV. On ISS, there's this receiver, sorry, a transmitter that they will send like, there's like a event. I'll show you in the workshop. You have to decode many of the pictures possible. So basically, in order to decode those pictures very clearly, you need to account for this Doppler effect. Otherwise, your picture gets skewed or your picture gets distorted. So I think I have some several examples for like Doppler related distortions. I'll show you in the workshop. And here, if you see, I mean, if you see it very carefully, I think you can see the Doppler one is changing quite slowly. And if you see the AO7, yes, AO7, okay, AO73. Can you guess whether this is moving towards us or not? Whether this satellite is moving towards or not? Can anyone guess? It's AO73. Is it moving towards us?
No.
Actually, the Earth is round, so basically, it's kind of moving towards us. If you see this polar part is very bit stretched, so that's why you might guess that as a no, but it's actually moving towards us. But it will be come to our like visible range within like six hours. That's the problem. So when it comes to like very close to our like location, this will change dramatically. Right now, the Doppler effect is very negligible. So that's what I want to point out here, because I mean, we'll be using this one like a lot in like in our decoding sessions on the workshop. I just want to like show there's a thing called Doppler effect and it will affect radio frequencies. I don't want to like go into maths for this one, and we have very limited time and we have to move to the other section. Actually, this Doppler corrected frequency is used to drive other applications. In this case, SDR-PP. This is like another application you can use to decode signals. So basically, this application itself doesn't have this Doppler correction capability. So we have to use gpredict for that one. So basically, the gpredict will feed this Doppler corrected one to this app, and this app will control the SDR according to the gpredict's Doppler corrected frequency. All I want to say is sometimes the pipeline means the software parts, it's not all in one solution. Sometimes you have to use several softwares for decoding some kind of signals, especially SSTV. You have to use three actually. I mean, there are like pipelines with like reduced numbers like two, but for my my way of doing it, I have to use three stuff: the gpredict, sdrpp, and SSTV decoding software. So I just want to point out there's this thing called pipelines. So, and the Doppler effect. I hope you might study this before you come to the workshop, and you might be able to notice the Doppler effect as well. If you see the spectrum that day, and let's move on to the other section. Just want to notice the effect of Doppler effect. That's it. Let's see. That's the presentation. Okay, that's gpredict. I think someone asked me about the gpredict usage. So I only use gpredict for the Doppler correction, and you can use gpredict to control a tracker. So basically, a pointer that will point your antenna towards the satellite. That function also capable within the gpredict's capabilities. And another thing I want to point out is all this information. Remember, I told you you have to remember this stuff: azimuth and elevation. So basically, most of the softwares use this format to specify the location of a satellite. Here also, the azimuth and elevation will be used throughout this session and during the workshop as well. And there are some other stuff here as well. And here they also calculated the Doppler effect for 100 megahertz. See, the Doppler effect itself is differ from frequency to frequency. So when you calculate in the Doppler effect, you have to account the frequency as well, not only the velocity. You have to count the what you call the frequency and the velocity of the satellite you are trying to get the signal from. And the next part, I think there are some programming students here. I think they can try this one within today as well. We're going to measure the location using a Python library. The library I'm going to use for this example is Skyfield. Prerequisites, obviously you need Python and you need Skyfield. I think most of you know how to install a Python library. If you don't know, if you successfully install Python, if you type this thing, I mean the code within the brackets, you will be able to install Skyfield with no problem. And you need a two-line element set, TLE. I think I talked about TLEs before, and I will talk further about TLEs in this part. So basically, what is a TLE? So a TLE is two-line way of saying where a satellite is and what is it about. So basically here, if you see below, this I have taken from this website called n2yo.com. So basically they have very up-to-date TLEs for many major satellites. Here this satellite is a geostationary satellite, very close to Africa and middle part of Africa, within Africa and Sri Lanka. So basically this is the TLE for that satellite. Here, I mean, if you see, I mean 36411. This is the catalog number of that satellite. Basically, you can't say the name of the satellite in this this TLE system is very ancient. So basically, it's very limited within in that regard. This U is what type of spacecraft is, and there are several other numbers here. I'm not going to deep into those stuff. And also, you can get these TLEs. If you remember the gpredict one. The gpredict one. Here, these TLEs are taken from, I told you, from URL links. So one of these repositories are SLTC. Oh, I mean, they have like up-to-date TLEs for most of the satellites. So basically, like softwares like GPredicts use those repositories to update their TLEs. So that's another way. And the thing is, these TLEs are only valid for 3 days for like low Earth orbit satellites. So basically, low Earth orbit satellites, they account many anomalies like gravitational anomalies and atmospheric drifts. So basically, this TLE is like a prediction system. It's like this is the last time from a known location how the satellite is in the space, and you can predict this from that point. You can predict to like a several days for like a lower orbit one, and for geostationary you can predict it for like up to 2 weeks, because geostationary satellites have like less effects. So basically the prediction can be like 2 weeks, maximum 2 weeks. So just some like more information for you. And here's the website, and I'll move to the website for you to know where the actual place the TL is. Can you see my screen? Hello.
Yes.
I moved to the web browser. So this GEOS is like a geostationary satellite. So if you go to a satellite, on the bottom part, there will be this TLE. I'll be using this TLE for demonstration of the Python script I'm about to show you now. Sorry guys, I didn't see. I mean, some of the guys have like sent messages, right? Let's see, is this white sky coverage as it is 1 point? Actually, no. Even though it's a VHF signal, you have to like point the antenna to a certain degree. I think this asked by MR Mihidi. I think I hope I can pronounce your name correctly. You have to point the satellite, the antenna to the satellite to a certain degree. I mean, I know, I mean, from like FM knowledge, you know, I mean, if you like put the antenna, you'll be able to like get the signal. I mean, with satellites, I mean, especially with like flying satellites, you have to like point the antenna to a certain degree, especially on gigahertz range. So even though this is on VHF range, still you have to point the antenna. Quadrifilar helix antenna or turnstile. You can use both. I think. Sorry about that, guys. I didn't see some of you guys have like asked me questions. So
Excuse me.
yeah.
Can't we use SatNox to read other satellites' data?
What?
SatNox?
I haven't heard that one. SatNox. What you? I mean, it's like a software or something.
It's an open source global network of satellites.
Actually, I haven't used that one. I mean, they are like repositories of like data you can get from internet for like several satellites, especially these NOAA satellites. I mean, they are like dedicated guys that have like it's like a mission to like it's basically something like that, I think. Yeah. So basically, yeah, it's like weather. Yeah. So basically, that kind of stuff. Basically, uh, you know, flight radar. So basically, they use the same technique to like gather data. They use volunteers to like gather data and make the aggregate themselves and show to everybody else to use. So basically, I think they have the same philosophy here for this SATNOX one. Thank you. I didn't know there's such kind of a effort there, to be honest. Thank you for that info. Actually, after this session, you might be able to like contribute to this SATNOX one, I think, at least for weather satellites. Thank you for that one, Samita. I didn't know about that one. So basically, we'll be using this. There's a gray line, to be honest. Flight radar. I mean, one of my friends recently, he is very close. I like within the footstep of the airport. And the problem with this is, I mean, you know, Sri Lanka. There are like many rules, especially when it comes to electronics. And the thing is, if you are like very near to the airport, Flight Radar will provide you with free device, and only you need like paid internet, and they will cover the entire fee, shipping to the device cost. But the thing is, you have to clear it from the customs. That's the problem. I mean, he got the stuff, but the thing is, custom is very thorough about this kind of stuff. So most of the time, you won't be able to get the components from the flight radar. But there's another thing. You can make an ADSP receiver by yourself. I think you have seen the first part of the presentation that I have shown you like a map with the amplifier and without the amplifier. Actually, that's a makeshift one. And the problem with this one is you have to be very close to the airport. Actually, far as I know, they have the most, I mean, like 22 receivers in like within Sri Lanka itself. Now they want to like improve the ground coverage. So basically, if you are like very near, actually like footstep like within like few hundred meters, you will have a higher chance of getting a receiver. So basically, I also like requested for a receiver. I didn't receive one, so I went to build my own. We'll be doing experiment of this ADSP one. You might be interested in that one in this session, because I mean there are like very few satellites. I mean you can decode using these SDRs. At least the SDRs we are like planning to use like RTL. So we'll be mostly focusing on like aircraft stuff as well. And yeah, I think hope you got your answer. Okay, let's move on to the actual demonstration. Can you see this code? I hope everyone can see this code. Is it visible? Now I'm in a Python IDE. Can anyone confirm?
It is visible, Mr. Mike.
Okay, thank you. So this is the script, like a very small script, but you can like get the location of the satellite with respect to your location. Here, this TS time load scale, it's like an internal time scale within the software itself of this API, Skyfield API. And you only have to provide the 2 lines of data, the TLE data. And this is a method they are using in this API, Earth satellite. I mean, there are like several stuff. I mean, celestial bodies. I mean, for this function, for Earth satellite related things, they have a separate function called Earth satellites. In that one, we have to insert this line 1 and line 2 of the TLE, and we have to give a nice name for this satellite. So basically, this satellite is EWS-G2. GEOS 15. This is a weather satellite. Used to be a weather satellite. Right now, it's like leased to US military, I guess. So basically, it's like still you can receive data from it. and this time scale. So you have to insert this one as well. So that's our satellite parameter. And here it's like a never-ending loop, and CT date time UTC now. So basically, every time the loop runs, it will get the current time, and it will convert it to this UTC time format. And your location, this WGS84, this is like a Earth model. You know, Earth is not a round one, as in sense, I mean, like a sphere. So basically, this WGS84 is a model of way of like saying how rough and how high the Earth is. So basically, this Skyfield API use this model to like get the location. So here I have insert, this is not my home location, if anyone is wondering. So basically you have to put your coordinates and your altitude for this one, and it will do some clever mathematics, and it will give a difference. This difference is the view from the satellite to your location. And then after that, after some another clever mathematic tricks, if you give the exact time, it will give the altitude, azimuth, and the distance from the satellite to your location. So basically here I have put some like if condition, if the satellite itself is over the horizon. So basically 0 degrees means, I mean, the horizon. So it's the altitude. Altitude, if the altitude is minus, it's below the horizon. That's one important thing you should remember about satellites. If the altitude or the elevation is minus, that satellite is below the horizon. You won't be able to see it. If the altitude is a positive number, that satellite is within your range. Actually, 0, I mean, is like, even though it sounds like within the horizon, still, I mean, very hard to capture from other end to the other end. So basically, you have to wait till at least 20 degrees for a satellite for us to like get the data from the satellite. So basically, let's say around like 10 degrees of altitude, so elevation, it's very hard to get information unless you are in like a very big field. There are like zero obstruction. So basically I just want to like point out that minus means like below the horizon, positive means above the horizon. So basically this will run forever until I tell it to stop. Let's run it and see what will happen. So this is a very recent TLE. So it's jotting out the location like every 0.2 seconds. Pardon, my laptop is very slow. And you can see, if you see closely, please start. Yeah. There's a slight variation. Let's see. There's a slight variation. Here. See, even though this satellite itself is geostationary, there's like a 0.7 variation, because even though the geostationary satellites are like very like, for us it's like very stationary, but they have like a little bit movement, 8-figure movement we call it, that called the envelope in like satellite terms. So box, envelope, box. So basically you have to like point your dish to the middle part of that box to get the most successful compromise between signal strength. So here the EWS at this point, it's like 69 degrees. Can you tell me this is above the horizon or not? It's like 69 degrees.
Excuse
like,
me.
yeah.
I don't know. Others can see, but I can't see the output of your program.
Sorry, my mistake. Thank you for pointing out. It's on a different window. Can you see it now?
Yes.
Hello. Yep. So basically, I'll explain it again. Here, the altitude, it says 69 degrees. Can anyone tell me whether this satellite is over the horizon or not?
It's not.
To be honest, it's over the horizon. You can see it, not see it. It's within our sky. As I mentioned before, altitude, sometimes it's called elevation as well. The altitude is actually, it says in this title as the EWS-G2, geos 15 is above the horizon. So basically, if the altitude is a positive number, you can be sure that the satellite itself is above the horizon. And that's kind of like a basic thing you have to like understand about this one, and your satellite tracking journey will be much more easy if you like understand that minus means it's below the horizon, positive means it's above the horizon. So what is this azimuth? Azimuth, I have explained it before. This azimuth is it's relative to true magnetic north, azimuth. So basically, it's like from north, if you take the clockwise direction, this much of angle you need to move, like turn. And then you have to look up 69 degrees and you will see the satellite. I mean, that's like if you put it in very layman terms, that's what it is. Like you have to turn 251 degrees clockwise and look up 69 degrees up, and you will see the satellites within your view. So basically, we can use this information and we can turn a tracker, like antenna tracker, and you can like accurately pinpoint to a certain degree. I won't say, even though the software itself has given us all this value, tracker has to be, the tracker mechanism has to be like very precise as well for us to like get a proper signal, and you will be able to track the satellite. So basically, it's like there's like a very small movement. That's what I'm going to point out here. I mean, that's another way of like calculating where the satellite is. So I have shown you like three ways. This is one for the like software guys for you to try out. I think I'll send the code itself so you can try it out yourself on a future day. So because come on, we are like learning to like towards to become engineers, and if you use the same map and some other guy with no idea use the same map and says, okay, I think everyone can understand single app එකක් ඉතින් ඔක ලොකු දෙයක් නෙමෙයිනේ කියන්න පුළුවන්. So someone can say, okay, it's an app, so why would you need the engineer for that? So that time you can like use this thing and can make them confused, and you can see that you can use this Skyfield app for like many of the stuff. If you can integrate like motors and Arduinos, you can like make an actual rotor with this one. We won't be doing it on the workshop, sadly. If you like wondering if you do it on the workshop. So basically, this is another way. We won't be using this one. We only be using the first and the second method. So let's move on to the slides again. So that's the script. And let's compare the results. All these results, I have taken here, I have taken all these results in the early morning today. Basically, if you can see the local time here says 11 and 36, 11:39. So basically here it's also the same. So very within like 5 minutes of time. If you see here, if you go to the azimuth on the website I have shown you earlier, you can see the elevation, the azimuth, so like 243.9, and the elevation is 67.3. And if you move on to the app, actually this one used like my IP location, so this is like little bit drifted apart. But if you like give it the actual coordinates, it will like well within the range. So still, if you see the altitude here, I have zoomed the app's altitude part here. It says the altitude is plus 86. So basically, very minimum difference. And if you go to our software, actually the script, you can see it's also 86 degrees. So basically, these are like very well within the same range. So basically, what I'm going to like point out here is, if you like try hard enough, you can make these are like very sophisticated apps. This one and these websites, they are like they are like very dedicated teams behind these kind of apps. But here, as a, like a simple programmer with less knowledge about like very like rocket stuff, we were able to like guesstimate this to like very within this range of paid app. This is there's a free version, don't get me wrong, there's a paid app version, but still you can get all these details in the free version as well. But still I want to point out, if you like try hard enough, you can get this data for free. So that's the main part here as well. We want to be cost effective as possible, making this ground station. So basically, I have shown you 3 ways to capture where the satellite is, basically how to track a satellite. And now where the decoding happens, I think someone asked about the decoding part, and now it's the part here, the decoding software. For this one, I'll be using SatDump. It's like a very latest software. Before this one, the weather satellite decoding game is like very hard. You have to have like several apps. I don't know whether you know SDR Sharp or like other like SDR softwares. You have to use those softwares. But here, this SatDump is like an all-in-one solution. Remember, I told you about pipelines. This SatDump is like a single software. The entire pipeline is within the software itself. So you don't have to like connect several softwares together. So that's why I have suggested using this SatDump software. This is a free software. Actually, you can download it for free. I hope you will be able to download it before the actual workshop itself, because I mean, we'll be using SatDump to like decode some satellite radio stuff. And the best thing about this satellite is very easy to use compared to other solutions. I mean, other solutions you have to like add TLEs and like other configuration stuff. With this SatDump one, all those configurations are built in, and most of the stuff is like already configured for us. So we have to like have like less stuff to worry about. We can like focus more about the signal receiving part. And another thing is, even though we are using like small bandwidth satellites, there are like some satellites that have higher bandwidth. Actually, it's impossible even with like very best computers to decode these satellites with high bandwidth in real time. So basically, you have to actually record the actual bit stream. So in this case, we call this the baseband. You have to record the baseband. So this software supports both offline and real-time decoding. So, and best part is it's free to use. And this is the interface. I mean, this look like some like military kind of screen. I mean, like a 90s type of vibe. And here you see offline processing. This SatDump software has built-in decoders for like many satellites in our sky. Some of them are like very hard to capture, and some are like there's no point decoding. We won't be able to decode the actual data itself. We can't make use of the data, but still there's possibility. They have given us the possibility to decode at least the baseband. So basically, this is the part where we be using. If you are like into like very high bandwidth satellite, you have to use this offline processing part. But in this case, we will be using recorder. Nova one is like very small bandwidth. So basically, we can get away with this real-time decoding part. And let's move on to some decoding. So basically,
Excuse me.
yeah,
What about WX 12mg decoder?
actually, it's like a very famous one. Sadly, it's no longer maintained, I guess.
Should we
I
have
have
to
used
use
it.
a high bandwidth for that?
What?
Should we have to use a high bandwidth for that when
For
comparing to SATDAM?
Actually, I think you have like the same bandwidth, if you're like referring to the bandwidth of the satellite, but here this software is bit process intensive, to be honest. Uh, but the actual satellite bandwidth is the same. So, and this one has like made everything very easy. So basically, if you are getting into satellite things, I mean, it's very easy for if you are using this. And if you see, you can see the Doppler effect here. I mean, right now the actual frequency is like little bit shifted to like right side of the spectrum. Here, the actual marker is like, if you see, it's not in the middle. So this is a bit of a Doppler related stuff. And there might be some, oscillator frequency drift as well, but it's mostly a combination of two. That's that. I mean, I think I've told you that you'll be able to see it during decoding. So here, I mean, it's like very apparent here. So here we are using Nova 90. So if you're wondering, the SAT parameters are same. Only the computational power is a little bit high for the SAT-DUM software. Other than that, everything is same. I think hope you got the answer for that one. So here we have the location of the satellite. This crosshair is the middle part of the crosshair is our location, and with respect to our location, this is north pointing. So basically, it's almost coming from Jaffna side. So basically, north part of the country, and will be like very close to our home, my place, and it will move like this. So it's like a elliptical pattern. So basically, here they have like dedicated decoders for NOVA. It's called NOVA APT demodulator. So basically, APT means automatic picture transmission. So basically, it's a very ancient type of transmission, but NOVA still use it up until very recently. So this is one of the views you can see when you decode it. So all this time I only talk about like theoretical and a little bit practical. So basically here we are going to be a little more practical. So this is the recorder part. I think I've told you recorder. So basically this SATDUM software capable of receiving AirSpy Mini and RTL-SDR. So see, there's a little bit difference between these two. I mean, even though the devices are this, I mean, SDRs, the AirSpy Mini has like much more like controls and toggles compared to RTL SDR. And this yellow offset, if you are wondering, that's the frequency or the oscillator drift I was talking about earlier. So if you see the signal itself is drifting like further away, you can use this yellow offset to like counter that problem. Otherwise, the decoder won't be able to decode the actual signal properly. So basically here, you can see the sample rate. I think if you have remember earlier, when we compare the two, I mean, I told you the Aspire Mini has like higher sample rate compared to RTL SDR, as you can see here. And for the Aspire Mini, they have like given us some more like fine tuning, granular fine tuning stuff here, like some like 3 radio buttons. So you can like select how do you want it, a linear sensitive. So basically here I have selected sensitive because we are dealing with like very low power satellites. So basically that's why I have put sensitive. And if you can see, it also has a gain. I have increased the gain to the maximum at the highest 21 dB for the Aspire Mini. And here, I mean, I didn't use any gain because I mean, there are some like problems with the RTL SDR itself, and it has like an already high gain. So I haven't used that part yet. And this is like a demonstration purpose. So I just want to like show you that even though, I mean, it says device, if you plug the different device, you might receive like different capabilities. That's what I'm going to point out here. And that's that. If you're wondering this frequency, this is one of the ATP frequencies of NOVA. And after that, we have to like give the data itself to the satellite data, so frequencies and stuff. If you see this NORAD, here, no, NORAD, so only 2 NORADs. These items, sadly, even though this like entire presentation is about NOAA satellites, all those satellites are now decommissioned as of 2025. That's the sad part. Even though this entire thing is about NOAA and better satellites, but Russian satellites are still operational. So we will be doing our actual workshop using Meteor satellites. Sadly, if anyone wants to like was like waiting for us to like decode, actually no, 21. Those are like very recent ones. Yeah. I have some decoded images. I will show you at the workshop. And there are like decoded images on like this presentation itself. And NOAA 21 is like a newer satellite. These are like newer generation of satellites. Sadly, this NOAA 20 and 21 satellite doesn't have this APT transmission capabilities. They are using L-band. So basically, L-band is like much more higher frequency. It's in like 1.4 gigahertz range. So basically, and you need like a satellite dish itself to like receive those signals. Because as you know, with the increase of signal, the directionality will increase. So basically, you will need a dish for these type of signals. Actually, I just want to, yeah.
S band is much more powerful than L band, or L band is much more powerful than S band?
It's like a very like a gray line there. To be honest, both of the frequency are within like very close. L band is 1 point like it's like 900 megahertz, something like that, and S band is 2 gigahertz, something like that. So basically, even though like they are very close, the problem with this type of thing is actually it's not the power itself. It's about all about how much you can collect, how much signal you can collect. Actually, if you see a satellite dish, actually that bigger dish part is actually the collector. Actual antenna itself is within the focal point of the dish. I mean, if you see, I mean, if you like broke the normal like don't broke your dish TV antenna for to see this, I'll be able to like get some LNBs if that's possible. You will see the antenna itself is like a small wire. You'll be surprised. Actually, it's like a normal, like a single strand of wire. I mean, if you have like 2 polarizations, it's like 2 wires. Actually, the problem with this and okay, that's a big gray line there. To be honest, if you are like doing that, actually don't do it. It's kind of illegal here. and that's a very big gray line, to be honest. Actually, there are like decoders you can buy, and there are like free TV satellites. Actually, there are several TV satellites you can like decode for free. You don't need any like payment or subscription to like a satellite company. You can decode them for free. They are like mostly news channels, but still fun to decode. And you can get a decoder in like beta market, but they are like very convoluted. I will not suggest to buying those things because I mean most of those are like illegal in the sense in Sri Lanka. To be honest, I mean when you're like doing this radio stuff, better to actually have like a radio license because most of this stuff is like very hello, am I audible to you? Yeah, FreeSat is like one of those main like satellite providers. Their price lately, but yeah, you can use FreeSat. Their decode is about like a few thousand rupees. Sadly, I won't be able to like comment on those stuff in this like since the lecture is public. So I'll be like sticking to like only mainly satellite stuff. Let's talk about those TV decoding stuff on the workshop itself. So since this is a recording, and let's move on to the actual weather satellite part. So basically, we have like this NORAD. Sadly, NOAA satellites are no longer operational. All I want to say is meteor satellites are only the operational ones for our use case. And since you guys have asked me recorded demo, actually I have recorded one. If you guys have like headphones, like try to like reduce your volume because I'm going to play a video and it has a very screeching noise. Let's talk about stuff in actually there are like very like LoRa guys, I mean very experts in our RSSL group more than me. Actually they have like actually working stuff. I mean, they will be, I mean, one of the guys will be meeting at the workshop, will be like, he's like a very expert on this LoRa stuff. And you'll be get your answer there. To be honest, actually, it's not about the frequency. Actually, it's the gain. And if you use a Yagi, your directionality will be like reduced very much to a certain direction. Starlet. Okay. The thing is, I mean, if you like using LoRa for like normal purposes, you will be need like more gain rather than a Yagi. If you like using like satellites, it's a different story. You will be needing a Yagi. Other than that, mostly you need gain, and with gain, there are like certain limitations. You can go with those gain as well. You have to like check for those limitations as well. Everything with like RF, we can't use the entire power we have. Each frequency band has their own. Uh, to be honest, I think the problem itself is have you like tuned your antenna properly? Because in this actual section, there in this presentation, I'll be showing you like a screenshot because today I have like decoded the meteor satellite itself for this very presentation, and I'm going to show you the decoded part, and we'll talk about this one on the workshop day if that's possible with you, if that's okay with you. Or let's move on to the actual video demo I want to show. Where's the desktop? Can you see my desktop? I hope everyone can see my desktop. If you are like wearing headphones, like reduce your volume because this is like very loud. Let's see. Hope you can see this video. Uh, can you guys see this video?
Yes, the video is
Yes.
visible, Mr.
Okay, since all this time I only like talk, there's no showing. So basically, this is like a live decoding of the Nova 19. Sadly, the Nova 19 is no longer operational. For the sake of this complicity of this, I mean, presentation, luckily I have recorded some like early Nova decoding, live decoding. So if you hear this sound, can you hear this sound? Uh, can anyone like tell me, can you hear the sound?
The audio we cannot hear.
Uh, okay, wait, let me see. Can you hear it now? The like a decoding sound other than my voice. Okay, wait.
Mark, we are still unable to hear the audio recording. Maybe it's because you have not shared the audio on Zoom. Unfortunately, we are unable to hear your voice now as well.
Can you hear? Can you hear now?
Yep, you're audible now.
Sorry about that one. I think I have talked you for like several minutes without like knowing that the audio also muted. So basically that's that. I will show you this again on the workshop day. Sorry about that one. That's my mistake and I apologize for that one. Not for like configuring for the audio part. Let's move on to the presentation. So where are we on the presentation? So since someone asked me, this is what you get if you like get a proper decoding. So basically you will see, okay, this is like Jagger. How did this turn into this one? If you notice, there are like these stripes on either side of this picture. The software use this feature and it will straighten the image to this one. So basically it will be like normal viewing conditions. So basically it's like skewed. So this will like sync that pattern. There's actually a pattern and this has some encoded data about the satellite and it's like some other stuff. And this marker is like a minute marker. So basically, even though we like, it's like a very continuous moving signal. We only receive part of the signal, only the part of we are like able to see. So basically here, if you can see, this is our country, Sri Lanka. So there's like a very cloudy around India. And sorry, I'm not an expert in meteorology, so I don't know how to explain the entire stuff on this, like in this weather image. Sorry about that one. Actually, these weather images are actually used by actual meteorologists to predict weather. So here we only talk about the actual decoding part. So that's how we decode it. Will Yeah, this is like a repository for that one. I think I have heard this one. And you can like get this NOAA data. I mean, it's freely available. I mean, decoded data. I mean, it's like an archive at this point because they are out of commission. So if you think this is the only thing you receive, you will be mistaken. And there are like more other stuff. Uh, I'll check this one. I think it's the same one I'm talking about here as well, the Copernic one. And let's move on to what else. I mean, the NOAA satellites capable of giving you other information as well. I mean, APT transmission is the most most famous one. Other than that, there are like other stuff as well. These are on like a several, I mean, different frequency, but you can decode them because I mean they are very close to the actual APT transmission frequency. So basically, you can decode them both. I mean, each and every NOAA satellite has this uh, data as well. Some equipment is like no longer, actually the NOAA itself is no longer uh, active. Even at the time of the decoding these stuff, some of the equipment are inactive. So basically, these are like three stuff I was able to like decode successfully. And sadly, this NOAA is no longer possible. So what we gonna do? Shall we like postpone or cancel the workshop? No. And we have Meteor. Actually, to be honest, today in the around like 3:30, there was like a Meteor pass. I was able to decode the Meteor satellite today. So basically, the Meteor is like Russian counterpart of NOAA program. So basically, these are like USA and Russia. You know, I mean, they are like a very frontier in this space exploration. So both have their own like weather satellite programs. So basically, Meteor is the Russian version of NOAA. So sad thing about is these NOAA satellites work on like very old transmission systems, automatic picture transmission. But these Meteor satellites, they are use a different modulation scheme altogether, LRPT, so low rate picture transmission. Don't get fooled by this low rate. I mean, they are much better than what you get from NOAA. So basically, and their signal is a QPSK signal, and NOAA has a FM one. So basically, there's a bit of difference. And for us, there are like two Meteor satellites. Actually, there are several Meteor satellites, but only two are operational at this point. So we can still use them for the foreseeable future if we are lucky. And can you guess? This is I have decoded today at 3:30 p.m. It's like few hours before the actual presentation. I was able to decode this stuff. So here, if you see, today is a cloudy day, right? According to this satellite image, it's also cloudy. And if you see, I mean, this pass went, yeah. I mean, sadly, I mean, sometimes if you can you guess the elevation, the highest elevation here for this session for the satellite pass? It was like 23 degrees. As you can see, even though it's 22 degrees is like very low. Actually, it seems like for hours in like normal convention, 23 degrees is like very low. I mean, it's not that high, but still I was able to capture this data transmission. And there's another interesting fact. I mean, actually, it's update with time to time, and actually, I haven't checked it very recently. And orbital inclination, usually we talk them for like like geostationary ones. That's why. So, and this is like sun synchronous orbit. So basically, special thing about this Meteor and NOAA satellites is they will cover the entire globe, uh, every place of the globe within a day. They usually have like a time period of 90 minutes. So since I mean every person in Earth, if they have like a receiver, they can get the data from any of these satellites at least once a day. Sorry about this orbital inclination. I don't remember it, and it's not very related to like solar synchronous orbits. But let's move on to the actual Meteor one here. So basically, this is like a very high resolution image. I want to point out. See, if I have cropped this part and still it's visible, like you can make sense of the features. So, and this is the next generation. And there are like satellites that we can get more frequent, I mean, more resolution than this one as well. And these satellites, I forgot to mention, even though we are only talking about VHF part, actually these satellites have L-band transponders as well, transmitters as well. They send more resolution, high resolution data on these bands as well. So, but we are only like talking about this VHF band because of the limited resources we have. But if you have like high power SDR with high bandwidth, you are certainly able to decode L band as well. So basically, this is LRPT for you. And don't worry about that. NOAA is like out, but still we have Meteor, the Russian counterpart. So we will be decoding this one in our workshop on the 12th. And this is like a picture. I mean, this I was taken when I was like decoding, actually receiving the signal. Remember, I told you that I will show you a way to like make a makeshift antenna. Actually, sorry, makeshift tracker. This is part of that makeshift tracker, and this is the actual like program. I mean, the app I have used for this tracker. Remember, I told you to download, if possible, download this app. So basically, if you can see, there's clouds as well. So basically, the satellite image is like very close to what you see on the ground as well. It's very cloudy. This is westbound. This is actually west side of the sky. So basically towards Africa. So actually the satellite is like flying over like westbound. And this is what I was able to get. Don't be fooled. Actually, only the actual images are only like two images actually. This MSA and MUSR RGB, sorry, MUSR R1. And these are like, others are like composites. Actually, all these satellites they transmit images in false color. And even NOAA, they send data in like, if you like see the actual raw image, it's black and white. So the actual software interpret that stuff and make the necessary adjustment to make the vegetation available. Like you can see it like in false color. So don't be fooled that these satellites send data in RGB like in normal sense. So basically, this is like I'm showing you how my makeshift tracker works. And in the more info part, this is the actual tracker. You might be laughing, but I was able to like get the actual Nova and the recent one, the Meteor one. Yes, you can use GNU radio, but it will be like very slow. And this, I don't know, you know this stuff. I mean, this uh, SATDAM software, it's based on like on what you call OpenSSL. So basically, it's like using your hardware to the fullest potential. So basically, use your actual video card to decode these images. So other than your CPU, it's like very intensive programming. This guy who has like made this software has like used almost all the tricks on the book to like make it like more like efficient. So if you use GNU radio, you have to make this stuff by yourself. Uh, for this Meteor one, I'll give you a starting point. You need a QPSK decoder. So basically that's that. And you need Reed Solomon decoding. And it's like very complicated. For a beginner, I suggest you set down and you can move on to GNU radio. I mean, it's almost about learning new stuff, right? That's that. You can use GNU radio. And this is, believe it or not, this is all part of that RT-SDR package I have mentioned you about, like in the very early of this presentation. This suction cup, I don't know, it's possible to like put this on like other cases. Luckily for my phone case, this suction cup, like it's like a glove. So basically, if you use this suction cup, it won't be moving anywhere. And remember this direction. So usually when you like pointing out stuff, especially outer space, you have to have your antenna in horizontal direction like this, like I'm holding right now. And this wire is very important as well. You can like can't put your wire like any other direction. This is the optimal way you can put your wire. Actually, the optimal way is like straight line, but this is like a compromise. You have to like put your wire like this, like straight to the ground. You can't use it like bend over the wires or the antenna itself. So basically, this is like optimal position I am holding right now. So basically, if you have this setup, I can guarantee you, I mean, if you see my NOAA images, all those NOAA images were like decoded using this setup, tracking setup. And if you ask, how do you like track the software? Actually, you use your VR function on this software. You can turn your phone and see what's within that frame. So basically, I use the phone itself as a, like a crosshair, like a pointer. So basically, I was able to point it within to like a very precision location that I was able to decode that much information from the signal from the satellite itself. So another part, uh, you can use any other antenna, but the antenna has to be tuned to exact frequency. If you see here, the LRTP transmission frequency for Meteor satellite is 137.9. This is the frequency you want your antenna to be tuned into. If you see here, can you see this part, the pointer? Can anyone confirm? Because I'm going to like explain some very important stuff here. This is you need, I mean, in order to like receive your signal, you have to be sure this value is very close to 50. Can anyone like confirm? Can you see this part?
Yes.
Yes, it is visible, Mr.
Okay, this has to be close to 50. Can anyone tell me why it has to be 50? Anyone has any idea about that one? Because we are like bit far away from like almost half an hour, and I want to like make it like quickly as possible for you two guys to like go to sleep. Can anyone guess why it has to be 50? Right now it's around like 48.62. It's very close to 50. Why we need to have it to around that part, like 50?
Because the radio input must be 50 ohms.
Yeah, exactly. One thing I haven't mentioned you guys still is all these STRs, they are expecting a 50 ohm impedance input. And sadly, antennas, you can't make them like behave 50 ohms all the way. Sometimes if you move the antenna a little bit here and there, this impedance must, I mean, can change. So basically here, it's like a real part is 48 and it's imaginary. It's like inductive part is 0.6179. So like a very close, good one, because in order to like receive something, you have to have this impedance very close to 50, at least close or like on point. On point is very impossible to do, at least very close to 48 or something like 55, something between that range. Because I mean, since we are receiving set signals, this one is very important. You have to have like a very tuned antenna. That's why I was able to like get this much of information out of the actual signal itself. It's one of the reasons, and the tracking part. And if you see, I mean, I haven't used any amplifiers. I mean, the set itself is like outer space, but still I was able to get that much information from the satellite. Actually, you are talking about something else. Actually, it's the gain of the antenna. Usually, we are using a dipole. It's like 3 dB or something gain. It's not minus, to be honest. It's like positive. But higher the gain, the higher the directionality is the antenna. If you use a Yagi, you have to have some better pointing ability than this dipole. Sometimes using higher gain is not beneficial if you don't have a higher accurate tracking system. That's why here I have used only a normal dipole instead of using a Yagi. That's one of the reasons. And sometimes you think higher the gain the antenna or Yagi, you can get like a good signal. Actually, it's not true. You have to have like a very good tuned antenna. Sometimes Yagis, I mean, especially when you are using for sat receiving, if you can't point it to like proper direction towards the satellite itself, you will receive half of the signal, or you won't be receiving signal at all. So with this dipoles, I mean, at least in this range of frequency, at least in VHF, it's very easy to use a dipole. Very like good, highly tuned dipole is much more effective and less problematic compared to like a Yagi. Especially like if you like increase the elements of the Yagi, you will get gain. But unless you know how to point the antenna, that gain is wasted. That's that. So those are the two main hurdles. I'll be showing you how to like the actual setup, because I mean in this presentation it's not practical to like show the actual video. In the actual workshop, I'll be explaining how to like make that tracker using that software. It's like a very like a nifty thing, nothing complicated. Like using the actual VR itself to like makeshift tracker of the phone. So that's all the caveats I want to talk about here. I think I covered some broad range of stuff, like glossly, like went through all the stuff. I think if you have like some exposure to satellite, you got some good stuff from this presentation. We'll be like doing most of this stuff we have talked about in this presentation in the workshop, especially the ADS-B one, because unlike satellites, aircrafts are like flying all over the place most of the time. And sadly, plus our selection of these satellites is limited to two now, because the Nova satellite constellation, at least the older Nova constellation, is no longer operational. So basically, we have to use these meteor satellites, so that leave us with less time to do practicals. So we'll be mostly focusing on ADS-B stuff, and let's try to do that hydrogen line stuff, but I don't sure it will be working around your campus premises. For now, let's do the satellite part and the ADS-B part. If you are like wondering, those are the two main things we have planned to do. That's that. Do you have any like other stuff you want to ask? I do my best to answer your questions. And it's like, actually, I was like planning to complete it at around like 7 actual time itself, but there's like another, like I completed after like half an hour almost. So any questions, if you want to ask, this is the time. Hello. So no questions. Actually, if you like shy to ask questions, I mean, you can ask me on the workshop day. That's no problem. Actually, we are like 30 minutes late. So, I mean, that's my presentation. I think hope you have learned something from it. Obviously, you are like very well knowledgeable about about satellite stuff, so that helped as well. Otherwise, I mean, that won't be like very effective because so many of you guys, I don't know it's the same person or not, you have asked like very important questions as well. So thanks for asking me those questions, and thank you for like telling me about that space like ADSB type aggregate for space stuff, space satellite as well. I haven't heard that one before. And thank you for your time. I think that's it for today. Let's see you on the actual workshop.
Thank you so much, Mr. Mike, for that fascinating and insightful presentation. I know our audience has learned a great deal. Now it is time for your questions. If you have any questions for Mr. Mike, you can scan the QR code on the screen to use Slido or simply drop your question in the Zoom chat box. We will answer as many as we can. I think the audience doesn't have any questions. If you all have any questions, feel free to bring it up during the workshop.
Ah,
We do have a question.
actually, the time dilation, actually, that happens because, I mean, like even though we can't see it, there's a curvature. I mean, there's gravity, there's curvature. So yeah, so weather satellites, we are not using like in the sense of atomic clocks. So basically, it's not that of a problem. But the only problem is Doppler effect. Not the only problem. Most of the problem is with the, I think I explained it in the presentation, it's the Doppler effect. So you have to account for this Doppler effect with like increasing or decreasing the frequency to match the actual frequency during that time. Other than that, unlike GPS satellites, time dilation is not affected phenomenon for weather satellites. Thank you. It's a very interesting question. I haven't thought about it like that way, to be honest. Actually, that's why we use 4 satellites. If you're wondering why we won't use like only 3 satellites. I mean, in theoretically, I mean, you only need 3 satellites, but you need a fourth one. That's one of the reasons behind that thing. Very interesting question. So I think there's one, I think I haven't used that Ravana or something. They have made one CubeSat. I mean, it's not like within Sri Lanka itself, but the project was led by like Sri Lankan student, I guess. I think I heard it. Like I haven't used like for communicated with the satellite, but yeah, I think it's Ravana or something. It's a CubeSat, I think. Yeah. I'm not sure. It's like Ravana or something. It's like very few years ago for Ravana, I guess. Yeah, sure. How do I put it? I'll send it to your like coordinators group. So one who like likes to like get the number, you can get it from him. No problem. Yeah, okay.
Thank you, everyone, for participating, and a huge thank you to Mr. Mike for answering them so thoughtfully. We are now ready for a small quiz session held via Kahoot. Get ready to test your knowledge. A very important announcement, a special notice for all participants. We are thrilled to announce that we are planning to provide 100% free boarding pass for the physical event to a selected quiz competition. Dear participants, please do scan the QR code on your screen. Dear participants, the quiz is about to start. Congrats, Asmita. You won the quiz. Before we move to our closing remarks, we would like to present a special token of our appreciation to Mr. Mike Shane. On behalf of the entire organizing committee, please accept this virtual trophy as a symbol of our deepest gratitude for your time, knowledge, and support in making this inaugural session such.
the kind appreciation token, or the winner gets some present or something for the quiz competition.
Yes, they will be getting. I would also like to take the opportunity to thank Ms. Prathana Lianage, the President of Radio Society of Sri Lanka, for her continued support.
Thank you.
Now, as we officially wrap up our second SATVISION webinar, I would like to invite our ground station manager, Damiru Dilmat, to deliver the vote of thanks. Damiru, the stage.
Good evening, everyone. Thank you to everyone who contributed to making this event a success. First and foremost, I would like to sincerely thank Mr. Mike Fernando for conducting such an insightful and engaging session on building a ground station and how space communication works. Your knowledge, experience, and passion truly inspired all of us today. I would also like to extend our sincere support toward initiatives such as this. In addition, I would like to extend my deepest gratitude to the organizers. Most importantly, I want to thank all the participants who joined us. Thank you, everyone, and have a wonderful evening.
Thank you, Damiru, and thank you once again to our wonderful audience for joining us today. This officially concludes the first session of SATVISION online series. Have a great rest of your day, and we look forward to seeing you at our next session.